Hey everybody, welcome back as we continue our study of transformations. And we're going to stay in the two-dimensional situation just to develop our ideas before we move on to the 3D transformations. So previously we talked about rotation of a reference frame. And just to recap, we said, okay, well, the white lines here are our original axis, and the yellow lines are our new set of axes, and we rotated our axes, our new set of axes, by theta from the original. And when we did that, what we derived were our x prime, which are our coordinates in our new system of a point. So if we have a point here, P, and we said that that equals, we got a little more sophisticated than that, didn't we? we got as far as working in the matrix solution, right? So we said that's x prime and y prime equals our rotation matrix, which was cos theta, sine theta, minus sine theta, and cos theta, times our original x and y coordinates. And when we gave those names, we said that was our x prime matrix, and that's our R matrix, and this was our X original coordinate matrix, right? When we performed that, we got a new set of coordinates, which were the, from in our diagram, that would be the coordinates of P in our new reference frame. So we have P, X, Y, and then we have P, X prime, Y prime. So new coordinates, same point, right? So that's what we did last time. Now we're going to look at what happens when we also translate that set of axes. So before we do, I have some helpful hints, because this can get a little confusing when we start talking about the direction of our translation and which reference frame we're talking about. This can get a little convoluted. So just some helpful hints to help us keep oriented. One, we want to focus on what is happening with just the origins of each frame, each reference frame. So we have our old reference frame, we rotate it, translate it up, and that new reference frame also has an origin. The reason that we only need to, well, let me get into number 2, and then I'll talk about the 1 and 2 are kind of tied together. So 2, the relationship between points in our old reference frame does not change with transformation. And to demonstrate that, let's say that we have some original reference frame here. And we have, there could be thousands of points, right? So let's just say we have a few points here. And in particular, there's another point that's going to be the origin of our new reference frame. So it's rotated and translated. But just because we've moved our reference frame, the relationship, the distances and the angles between all our points doesn't change. They stay in the same place. So the relationship between points in our either frame, no matter what, the relationship between the points themselves, if we were to remove the axes, we would see no difference. They would stay the same. So in this way I can say what that really means is distances and angles are preserved. Now, that can change as our transformations get more complex. If we start talking about transforming between map projections, that kind of thing, that can get more convoluted. But for what we're doing right now, distances and angles are preserved. However, there is a nuance. With scaling, the representation, can I fit it in there? Representation of distances, and I'll say reflected by coordinates, so communicated through the coordinates, might change but actual distance does not. What am I talking about? Well, when we scale reference frame, but actual distance does not. When we scale a reference frame, really we scale a reference frame in order to accommodate moving from one metric to another metric. So we're moving from feet to meters. So our old reference frame is in feet, our new reference frame is in meters. That would involve a scaling to get the coordinates to adequately represent the new metric of the new reference frame. And that's a pretty easy concept. We do that all the time. So really, even scaling does not affect the relationship between points. It just affects the units by which we represent the coordinates of those points. Important concept, okay? What did I miss here? I don't think I missed anything. So let's go on to the third helpful hint. 3. Be hyper-aware of perspective so that means, are we interested in, let's see, the coordinates of the old origin in the new reference frame, or are we interested in the opposite, or vice versa, the new origin in the old reference frame? So perspective is important, which we'll see when we get into the translation. Okay, the fourth tip is that order of events matters. Well, you know what? It doesn't, but I'm going to talk about that. So the order of events matters. Now, let's see. We can translate, then rotate, or rotate, then translate. And we can certainly do that. But the transformations look different. In the process, not the result. So we would apply different rotation matrices, translation matrices, depending on the order that we do it. Essentially, it doesn't matter which order we do it in, but if we have to execute the process in a different way depending on the order, why don't we just stick with the same order? It'll be a lot less confusing. So as a convention, so for this course, as a convention, we will rotate, then we will translate. And hopefully that'll become apparent as we continue studying this. And finally, helpful hint number 5. Be also hyper-aware of units. Feet, meters, miles, kilometers, blah, blah, blah. Be hyper-aware of units. We will be applying scaling slightly differently based on the units of our translation vector. And that will make sense when we talk about scaling. I'll revisit that so that we can be a little more clear on what that actually means. So be hyper-aware of units, as always, as we always should be and always do. We need to know what units we're working in. Okay, a little spot there. So let's start looking at translation. So to get the idea, let's look at just translation by itself without any rotations. Let me bring over a diagram here so I'm not trying to draw. So if this is our original system, and we have our origin here, and we want to translate to a new origin, O prime, then that new origin has its set of axes. I'll just draw them smaller so that I don't, come on, shoot. Sometimes this thing is a little laggy. Just trying to draw a set of axes here. So there's my new reference frame with its new origin, and there is a vector between those points, right? And I'm going to keep saying vector because it's going to become very crucial that we keep track of the direction that we're moving, okay? Think of it kind of like latitudes and departures. The positives and the negatives of our result makes a difference. So if that's our vector has components, right? So if I draw an orthogonal projection down, then this would be the x value, or the translation component in the x direction. And over here would be the translation component in our y direction. And I could reflect those up here as well, right? This would be tx, and this would be ty. So our translation vector, that's our translation vector, which is moving that way, is equal to tx and ty. Just different symbology, but something we've been doing since, 5th grade or whatever. Those are just coordinates, aren't they? So the O prime in the old system has coordinates tx and ty. And since direction is important, we notice that here in our development right now, our tx is in the positive direction and our ty is in the positive direction. Now there's also a t prime vector, which is based on going the opposite direction. So that would be tx prime, which is in that direction, and ty prime, which is the opposite direction. That would make up the vector from O prime up here down to, that becomes that vector, right? Down to O. Okay, so direction's important. I want to be really careful with this diagram because the tendency is to say, oh, well, tx prime just equals the opposite of tx, and ty prime equals the opposite of ty. And that's certainly true in this case, wherein we have no rotation. This is only true if no rotation. It's a very special case, which almost never happens. So we don't want to think of our translation components as being opposites of each other, positive and negative. We don't want to think of it that way. All right. So the question becomes, once we've performed our translation, I don't want to use that color. What are the new coordinates once we performed our translation of O, which is our origin of our old frame? What are the coordinates of that? Well, remember, O prime, once we performed our translation, is at 0, 0. So to get from O prime to O, we have to go t prime of x and then t prime of y. So be O prime, let's see, How am I going to write this? Let's see. O, new, I'll say, because we already have O prime taken, equals tx plus tx prime, right? Because we're going this way. We're adding, so tx would be negative, so we're going to add a negative, and ty plus ty prime. That's the idea we're going to develop. Now, that's just sort of a nutshell. Let me go find the other diagram I want to use. So I'm going to scoot that off. Don't need to use that anymore. Erase all this. And I'm going to go find my other helpful diagram. Over here, I'm going to pull it in. So this is just a slightly more detailed drawing of that translation once we've, so the gray lines, this is our old reference frame. And these yellow lines, that's our new reference frame. We've new. So we have rotated it by some angle theta, and we've translated it by some translation vector here, right? And we can start to see, and what I've done here, and this is why, okay, so we have our tx here and our ty here, and that's this whole thing. That's our tx and our ty. Well, once we're here, this, let me change colors here. This distance is our ty prime, and, or sorry, tx prime. And this distance is our ty prime. So that's why, and obviously, if you just by inspection, ty is greater than ty prime. So by inspection, with the rotation, tx prime does not equal the opposite of ty or tx, and ty prime does not equal the opposite of ty. They're different magnitudes and they're different directions. So now we have a goal. We already know how to rotate, but to translate, we need to derive tx prime and ty prime, right? Okay, I'm going to erase this because I'm going to approach this drawing a little bit differently. Now, this red line up here, this is going to be the same distance as our tx prime, right? So from here to here, that's tx prime. That's one of our goals. So let's focus on tx prime first. We know we have some similar triangles. So this is angle theta. This is the angle by which we rotated our axis. And we have some similar triangles. So here it should be easy to see that that's also angle theta. This is also angle theta. This is also angle theta. That should be easy to spell out. And this is our Tx, our hypotenuse here. Let me use a different color. That's Tx. And this is our Ty. Likewise, this distance over here is Ty, because they're the same distance, right? And that's Ty. Okay, well, from that, it's easy to see that the length of this would be Ty cos theta. Ty cos theta from here to here, just because that's a right triangle, isn't it? With a hypotenuse of Ty, so Ty cos theta. And what we're interested in is getting this distance and this distance, right? So that means that this whole distance here is Ty cos theta, right? All right, likewise, let me move that Tx prime up. So Tx prime is from there to there. If I treat this right triangle the same way, then I get this length is Tx adjacent, so adjacent is cosine, so that's Tx cos theta. And this would be Ty sine theta, because on this right triangle, I have Ty for the hypotenuse, and so this is Ty sine theta. So that if I add those together, I get Tx prime, don't I? So Tx prime, but now we have to think about direction. So if I add these, Tx prime equals the opposite of Ty sine theta plus Tx cos theta. And it's the opposite because Tx prime is going in the negative, quote-unquote, negative direction in my new frame. So Tx prime equals negative quantity there. And the same way, since I have Ty cos theta for this distance, I can subtract this distance to get my Ty prime. So the whole thing is Ty cos theta. So that equals, and again, it's going to be the opposite, negative Ty cos theta minus this distance right here. Which, what is that? Oh, that's Tx sine theta. Right? Because I have my theta here, my hypotenuse of Tx, so Tx sine theta. And if I move my negative in, now I'm just going to work with the equation, so I don't need the diagram as much. Then I get Tx prime equals Tx cos theta. That's minus. I'm trying to do this nice and neat so you can write it. All I'm doing is taking that negative in. So equals minus tx cos theta minus ty sine theta. All I did was move the negative in and into here. I moved the negative in and rearranged the terms just so I can have my x's and y's in the right order. And ty prime equals minus, oh sorry, it's not minus because I'm moving my negative in, so that's going to be tx sine theta minus ty cos theta. And these are the values we are interested in. We already knew what our translation vector was. It was the tx and ty. So we had our translation vector, we had our rotation angle, and we just derived the method by which we get tx and ty. Now in vector terms, I can say, all right, or in matrix notation, I can say now that our t prime vector, let me get there. So I'm going to spell it out here. Tx prime, ty prime is equal to cos theta sine theta and sine theta cos theta. Oh, I'm moving the negative out, by the way. Cos theta. All I did was pull that negative out, times tx and ty. All right. And all of that we would call our t prime vector. So right now, I think an example would be helpful. We always like examples because they help us out. Can help us to conceptualize what we're doing. So as an example, you know what? I'm not ready for an example yet because I want to develop the whole transformation equation. So rotation and translation. And remember, we're always trying to get these new coordinates. And from our rotation, we have, that is our rotation matrix times our xy matrix. Now all we do is we just add our t prime matrix. So we rotate and then we translate. And altogether that looks like x prime, y prime equals cos theta, sine theta, minus sine theta, cos theta. you're probably recognizing some similarities here, plus tx and ty prime. So there's my x prime vector, my rotation. Oh, I have to put my, forgot my original coordinates. That wouldn't be very helpful. So times x, y, my original coordinates, plus my translation vector, tx prime, ty prime. So that's my x vector, x prime vector, my rotation vector, and this is my original coordinate vector plus my translation vector. And just to rewrite that, I have x prime equals r x plus t prime. And that's what we're going to use to perform our translation and our rotation together. So now we can do an example. That would be helpful. Try to leave that up there. Example. So a 2D coordinate system, I'm going to say reference frame, is to be transformed such that such that theta, our rotation angle, equals 28 degrees. Our tx, in our original system, so our tx equals 41, and our ty equals 63. And the question we want, just for kicks, what are the new coordinates of the origin of our new reference frame? And you say right away, hey, wait a second, I already know what the coordinates of our origin of our new reference frame will be. They'll be 0, 0, because the origin of a reference frame always has 0, 0 as its components. But let's check what we just did and find out if that's the case. So I'll put should be 0, 0. So let's try it out and see if we actually get that. I'm going to move it up and I'll rewrite my givens. So solution. And theta equals 28 degrees. Tx equals 41. Doesn't matter the units, it can be meters or feet or whatever. And ty equals 63. We're going to use what we just came up with. Our x prime vector equals our rotation vector times our x vector plus the prime of our translation vector. All right, so if I write this out, I have x prime and y prime, which are what I'm trying to find, equal the cosine of 28 degrees and the sine of 28 degrees minus sine of 28 degrees and cosine of 28 degrees times our original coordinates, which were what? Our tx and ty, right? Because those are the coordinates of the original coordinates of our origin. So 41, 63 plus t prime x and t prime y. But I can just replace that tx prime and ty prime because we don't know what those are yet. We'd have to derive those. So what that comes to, what that looks like, what we found out before, plus the negative of cos 28 degrees sine 28 degrees minus sine 28 degrees and cosine 28 degrees times our tx and ty. That's what we derived above. See if I can find it really quick. Yeah, that's that right there. So all I did was just plugged that in for our tx prime and ty prime. And what are tx and ty? Well, we have that. So let me just stick those in there. 41, 63. Wait a second. If you notice, this is pretty special. This is exactly the same as this, but negative, so that equals the zero vector, or equals 0, 0, which is what we expected, isn't it? So x prime equals 0 and y prime equals 0. Those are the new coordinates of our origin in the new system, just like we expected. Now, I did post this example on Canvas. Let me bring it up. So this is what's posted on Canvas. And this is the example I just did, but I found the coordinates of a few other points. So I wanted to know the coordinates of the new origin in the old reference frame, the coordinates of the old origin in the new reference frame, and the coordinates of the new origin in the new reference frame. And you can walk through this on your own, but essentially I want to point out that here's my rotation matrix. I only have to do that once, right? Because my rotation angle of my new reference frame from my old reference frame doesn't change through a problem, right? So that's going to be constant for the transformation. And neither do my tx prime or my ty prime. Remember, those are based on my rotation angle and my original tx and ty. My translation vector doesn't change from point to point or from, no matter what we do. My translation vector stays the same. So that means that tx prime and ty prime would be the same. And I can use that information to do all my calculations for all my coordinates, right? So here, the is what we just did, and part C is what I just did on the blackboard or whiteboard or whatever it is. Come on, I want to highlight you. So C is what I just did, and all I did was I just put those matrix formulae into the solution, the yellow boxes. And then of course we always include the formula that we use, and that really makes it helpful for a quick reference while we're building these matrices in Excel. So this is on Canvas. I encourage you to reproduce it to get used to the transformation process of rotations and translations. All right, so finally, the last component we want to look at is scaling. Get rid of I keep getting these little specks in here. So scaling. What if we want to scale our translation? And let's just say by some ratio, some factor of S. Well, let's recall that we have our vector x prime equals our rotation matrix times our original coordinates plus the prime of our translation vector. Well, all we have to do is multiply by our scaling factor. And we use that form if and only if. Whoops. If we need to scale our translation vector. Similarly, our new coordinates equal the rotation vector times our old coordinates plus the prime of our translation vector. And I'm going to need more room in the beginning here, so I'm going to make a little equals. But if we only multiply our scaling factor to our rotated coordinates, we want to use that form if and only if we do not need to scale our translation vector. Well, how do we know if we need to scale our translation vector or not? If we're given the task of transforming a coordinate system that includes scaling, usually we're told something like our original reference frame is in meters, our resulting our transformed reference frame needs to be in international feet. And then we'll say, so translate by 5 meters. Well, in that case, we want to get that 5 meters into international feet, so we would scale the translation vector. If, on the other hand, we're told our original reference frame is in meters, we want our resulting one to be in international feet, and we are translating by 400 international feet. Well, we're given that translation factor already in international feet, the units or metrics of our new reference frame. We would not need to scale that translation vector. So that's the difference. And I think one more quick example before we call it a day. So scaling example. Let's see, example. We want to transform a reference frame with, well, let's see. Such that our rotation angle of our rotation of our reference frame is going to be 30 degrees. Our t prime x, so we're given our t prime x in this case, just to simplify matters, is negative 50 meters. And our t prime of y equals 50 meters. And our original frame, RF, is in international feet. Our new reference frame is in meters. So we're changing units. That means we want to apply a scaling. And that scaling, S equals 0.3048. That's the factor that we use to go from feet to meters. But here we see that our translation vector is already in meters. So we don't need to transform our translation vector. So that implies that we need to use, we need to use we get our new coordinates from using our scaling just our rotation vector. S times our rotation vector. I guess I didn't need the bracket there. Thinking matrices. Scale our rotation vector times our original coordinates, and then add our t prime, the prime of our translation vector. Cool. So we're trying to get new coordinates. So x prime equals 0.3048 times our rotation vector, which is the cosine of 30 degrees, sine of 30 degrees, and minus sine of 30 degrees, and cosine of 30 degrees. Times some original coordinates. We haven't decided what we're gonna transform yet. Plus tx prime and ty prime. But we were given those, weren't we? So let's just fill those in. (41) and 63. Cool. So the only thing we have to fill in are our coordinates. So we'll do that for several sets of coordinates. We'll start with point A, which has 0, 0, and that, we'll note, is the origin of our original reference frame, because 0, 0. B equals 60.044, and oops, I'm oopsing a lot, and negative 224.086, and C equals 12.000 and 12.000, and these are in international feet, right? Because these are the coordinates in the original reference frame. D equals -8 and 6, and these are just made up numbers, so E equals -50 and -50. So a bunch of random points. The only one that's not random is the origin of our old reference frame. Okay, and I don't want to do all those calculations by hand. I don't want to do them in on paper and with a calculator. There's just too much room for error. So let's see, I do have this on a spreadsheet. Bring up the, let's see. There we go. So here it is. Notice first of all that I have, I don't have my pen anymore. I have my formulae all laid out, and it's nice to do this ahead of time in your spreadsheet because it makes it super easy to reference what formula I'm going to use. And I'm just going to delete these and put a couple in and show you how we do this. And let's see, the example we're doing is part C. Parts A and B are for other coordinates. Am I in the right example here? I'm not in the right example. Let me go find the right example. Let's see, so there we go, here it is. So yeah, again, I have my formulae, very helpful, in fact, imperative. And then in the green boxes, I have my givens. And this is going to be my solution, so I'm going to make that a different color. Make that yellow and bold. Okay, so the first step would be to come up with my rotation matrix. Well, we know that. That's the cosine of theta and sine of theta and that is minus sine, that equals the negative sine of theta, or the opposite of sine theta, and cosine of theta. That's easy. And my t prime I'm given, that's -50 and 50, which that could be a green box, right? Because they're givens. There we go. So I have everything I need now to calculate what I'm trying to do. Now the first thing I note is that my translation vector is already scaled. So I do not need to scale my translation vector. So I'm going to use well, I don't have my S's in my formulae, but I'm only going to scale my my rotation vector. I'm not going to scale my translation vector. So if I do that, let me do A off to the side here. If I highlight, this is where it's necessary to come up with cardinality. So if my if I'm going by, let me go back to my whiteboard here real quick. I'll leave it here. I have a scalar, and my rotation vector is a 2 by 2. My original coordinate vector is a 2 by 1. And so my resulting vector will be a 2 by 1, which is a vertical vector. If I were to transpose this result, or plus a 2 by 1, that's going to equal some vector, that's a 2 by 1. And the transpose of that, I'll say tx, or that's x prime and y prime. X prime, y prime, my new coordinates. The transpose would just be a 1 by 2. So this is 2 by 1. The transpose would be 1 by 2. X prime, y prime. And that's going to be important when we build our spreadsheet. So I want this to be equals my scalar, see if I can do this on the fly, times MMULT, the product of my rotation vector and here's a little helpful hint too. If when you put in that translation vector, or the rotation vector, sorry, you put that in and you hit F4, it's going to make that absolute, and that's going to be really helpful. You want to get used to working with absolute reference or absolute referenced cells or dynamic reference cells. We're going to be using the rotation vector for all of these, so that would be static. So we're multiplying our rotation vector by our original xy. So there's my rotation. And then I'm going to add my prime translation vector. And that's going to be absolute. And all of that, now remember that if I just perform the transformation, I'm going to get a column vector, but I'm giving my result as a row vector. So I'm going to take the transpose of all of that. So transpose, shoot. I knew it would be tough to do this on the fly. So equals the scale times MMULT of that F4, comma, my point, plus the prime vector, which I want to make absolute. I also want to make my scale absolute though, don't I? Because I always want to be referencing the same scale, the same rotation vector, the same translation vector. And then I also want to transpose it so I get a row vector for the way I'm representing this. So equals transpose of the whole thing. And hopefully that will work. No, it didn't. Let me do this again. So this is going to equal the transpose of my formula, because again, we're building this into a row vector in this circumstance. I wouldn't need to transform it. In fact, I could just go x prime and y prime. In fact, let's do that. Of A, B, C, D, and E. And I could say, this is so I don't have to transpose in the beginning. But notice the points in the old system are in a row vector, so I do need to transpose those for the multiplication. So anyway, my point A would be equal to the scale, and I'm going to F4 so it's absolute, times the multiplication of my row vector times, whoops, not times, comma, the transpose of my original coordinates, because in order for matrix multiplication to work, my dimensions have to be correct, right? Plus my translation vector, F4 to make it absolute, close the parentheses, and there we go. So minus 50 and 50 would be my coordinates of A. And I could put those over here. I could say equals transpose. There. There we go. So a lot of the struggle here with Excel is just getting used to making sure your matrices are well defined and the operations on your matrices are well defined by applying the transpositions as is necessary. And I could do this all in one step. I think I will. Give it a shot. So equals transpose, because I need the whole thing, right? Of S, make it absolute, because I'm going to keep referencing that cell, times the product, the matrix product of R, hit F4 for absolute, comma, and my points, but it has to be the transpose of my points, right? And close all my parentheses for the multiplication. And then I'm going to add my translation vector, which I want to be absolute. And then I close, and hopefully, there we go. Now, since I made I referenced the cells absolutely that I want to maintain as I calculate the rest of these. Now all I have to do, if I manage my absolute cell references well, is drag it down, and let's see what we have. Yep, that's correct. So once we get the first one and you manage your absolutes well, then we're going to get all of the points. And that's the value of Excel, is you don't have to do as many calculations. Once you get an error, you can just fix it in one spot and then apply it to all the others. So this example is posted on Facebook, I don't even have Facebook, on Canvas. And I encourage you strongly to try to reproduce this. Try to really pay attention and work with those matrices in Excel so you can get used to that process. We'll be using that the matrix operations in Excel quite a bit. So that's it. That is the rest of the two-dimensional transformation with examples. The examples posted on Canvas. If you have any questions, of course, as usual, reach out, email, phone, text, and we can set up Zoom sessions or whatever. Meanwhile, we also have our weekly Zoom sessions, which you can take part on or request your own. And I'm going to leave it at that. The next time we will go into the 3D coordinate transformations. And I will let you know that I'm not going to go into this kind of detail. I went into this detail in derivation just in the interest of building that concept image of what we're doing and how complex it can be. It gets even more complex with 3 dimensions. So, you know, but it's all based in the same ideas. So I don't really want to use the same ideas in a more complex fashion. It's going to just bog the waters down. Anyway, so next time, 3D rotation, translation, and scaling, and we will see you then. Have a great day.